Okay, cool. I think the recording is going. Um, let's go ahead and get started. So this first problem, it says earlier in the year, UCSB established the COVID-19 early detection, testing, and monitoring program. The program randomly selects community members to take PCR tests for detecting COVID on a weekly basis. Assume that the PCR test correctly detects when a person truly has COVID 99% of the time. And suppose that a random community member is selected to take the test. Unknown to UCSB at the time, 5 in 100 community members have COVID-19. Furthermore, it is true that the overall probability of a positive test is 3%. And now we have a bunch of side questions. So these are all going to be probability related. So the first one is, what is the probability that the community member has COVID and we get a positive test result? So for probability problems like this, let me get this going. What we really should do is list out everything that's given to us to start. So, well, first, let's define what our events are that we're even working with. So let's call event A. So A is going to be the event where we get a positive PCR test result. So positive PCR test. And then the other event that's going on, we want to know whether the community member has COVID or there's a positive test result. So let's call B being truly positive with COVID. So B is having COVID. And now, in terms of A and B, the probabilities of A and B and all these different combinations we could have, let's list everything that's given. So it tells us that the overall probability of a positive test is 3%. So that's directly telling us that the probability of a positive test, the probability of A, is 0.03. And let's see, it says that unknown to UCSB at the time, at any given time, 5 in 100 community members have COVID-19. So the probability that a randomly selected community member has COVID-19 is 5 in 100, which is 5%, so 0.05. And then the last bit of information that we're given is that we assume that the positive PCR test correctly detects when a person truly has COVID 99% of the time. So unpacking what that's saying is that if a person truly has COVID, so given that the person has COVID, the PCR will detect that correctly 99% of the time. In other words, the probability of getting a positive result, given that you actually have COVID, is 0.99. So I'll make a note that these are all givens. So I would start out probability problems by listing all your givens. And then all the probability problems are going to be is just knowing the different formulas for like probability of like ands and or probabilities and given probabilities, knowing those formulas and mix matching and figuring out, which what thing can you make. So what this problem asks is it wants us to find the probability that the member has COVID. So B and get a positive test result, A. So probability of B and A, which, if you recall, that's equal to, well, something in terms of a given probability. You may remember the formula, that probability of A given B, the thing that's 99% over here. A given B is the probability of A and B divided by the probability of B. So if we multiply probability of B to the other side, we would see that probability of B and A, which is equal to probability of A and B, is the probability of A given B times the probability of B. So this is just what holds in general. And we have these two quantities. So we have that probability of A given B is 0.99, and then the probability of B is 0.05. If we multiply these two together, we get 0.0495. And so that's our answer. Now, moving on to part B, let's look. We have that we want to know what is the probability of getting a negative PCR result, given that the community member does not have COVID. This is also known as the test diagnosis specificity. And so let's write out mathematically what the expression would be that we're trying to solve here. So we've already listed our givens above, so let's leave that on the screen. We have that we're trying to find the probability that we get a negative test result. A negative test result is A complement, because A is having a positive result, so being a negative result would be A complement. I'm going to denote complement with a little c up as like an exponential. Now, this is with the information says given that community member does not have COVID. So this is given B complement. B is having COVID. So same formula that was just mentioned earlier. So we have the probability of A complement given B complement is the probability of A complement and B complement divided by the probability of B complement. Now, probability B complement is pretty easy. That's just 1 minus probability of B. But this top part, probability of A complement and B complement, what the heck is that? Let's draw ourselves a picture to see what this could be. So I'm going to draw over here this box for our probability space. And let's say we have one event, A, and then we have some other event, B. Then A complement and B complement, that means that we're outside of A. So we're anywhere outside of A, so outside of this blue circle, and simultaneously we're outside of the red circle, which means to be outside of both circles at once means we're, outside both circles. So we're in this exterior white region. So this purple region is A complement and B complement. So how would we find out what this probability is? Well, we can notice that this, the interior part of the circles where like the peanut shape of the two circles being formed together, that's the probability of A or B. So the probability of A complement and B complement is going to be 1 minus that peanut shape, which is the probability of A or B. And that's going to be divided by, again, the probability of B complement here in the denominator is 1 minus the probability of B. And now we can break up this or part. We can break up this guy with a formula. Remember that probability of A or B is equal to right over here. So it's going to be 1 minus probability of A or B can break up as probability of A plus the probability of B minus the probability of A and B. And then this is still divided by 1 minus the probability of B. And I'm running out of room here, so hopefully I'll be able to scrunch this down onto this last line. So now this is in terms of all numbers that we have. We computed probability of A and B here is the same number as the probability of B and A. Those are interchangeable. So we have all the numbers since we computed probability of A and B in the last part. So we have 1 minus, and the probability of A is 0.03 plus 0.05 for the probability of B, and then minus 0.0495. And then this is all over the probability of B complement, which is 1 minus probability of B, which is 1 minus 0.05. If we plug all of this into a calculator, I don't remember what it gives, but I worked out these solutions earlier, so let's take a look. We have 0.9163. So here this is equal to 0.9163. Okay. Any questions so far? All right, then let's continue. So next, we want to find the probability that a community member does not have COVID and we get a positive test result. So not having COVID would be the probability of B complement, and then it has a big fat and, so and we get a positive test result is A. So now, again, let's try to think of how could we use what we have to break this up. So whenever we see an A and B or whatever, something and something, most likely we're going to be using this formula up here, something like this. So if we were to think about, okay, what do we have? We have the probability of A given, we can break this up as probability of B complement given A, or we can break it up as probability of A given B complement. And because I know we just actually computed something with the given B complement part here, I'm going to be using that. So I'm going to break this up as the probability of A given B complement, matching what we found in part B. And then this would be times the probability of B complement. So again, if I were to just divide the B complement to the other side of this equation, that's the definition of conditional probability, or not definition, but one of the formulas for conditional probability explicitly. So it may not look like we have a lot here because A given B complement, what the heck is that? Well, let's think about what A given B complement means. So this is the probability of getting a positive test result given that the person doesn't have COVID. Now, let's think of what that is in relation to what we found in part B. Part B, this whole expression is the probability of getting a negative result given that the person does not have COVID. So if you think about it, given that the person doesn't have COVID, there's a 91% chance, 91.63% chance that we get a negative test result. That conversely means that there's a 1 minus 0.9163% chance that the test ends up becoming positive, right? Because given the person having COVID, they take the test, either it's going to show up positive or it's negative. And 91% of the time, it's going to show up negative if they have COVID, or if they don't have COVID, I mean. So the other bit, this essentially breaks down into being 1 minus the probability of A complement given B complement. And then this is still times probability of B complement. So this is equal to 1 minus 0.9163 times probability of B complement is 1 minus 0.05, because probability B is 0.05. So I, again, don't remember what this is equal to. And I can't swipe right or left if I draw on it for too long. It gets stuck on that page. So it ends up being 0.0795. So 0.0795. Okay. Now we're done with the probability problem. So again, I'll ask if there's any questions. Okay, so let's move on. Question 2. Well, I'll just mention with probability problems again, biggest thing you can do is list out all your given probabilities and then, just try a bunch of different formulas and draw diagrams to think, just like how in part B, didn't know what A complement and B complement was. So I drew a diagram to figure out what it would be in terms of other things that I do know. And so, yeah, that's really the strategy for going about probability problems. So question 2, the official course length for the Big Sur International Marathon is 26.20 miles. However, the course is measured on a very particular path, and given that the runners are zigzagging across the road throughout the course, from passing other runners, stopping at aid stations, etc., most runners end up running further than 26.2 miles. The finishing distances by runners during the race is normally distributed with a mean of 26.4 miles and a standard deviation of 0.03 miles. So what is the probability that a randomly selected runner runs at least 26.36 miles? So this is just a standard normal distribution probability problem. So let's define X as this normal, or as a random variable with this normal distribution that has a mean of 26.4 and a standard deviation of 0.03. Then the probability that we're trying to find is the probability that the randomly selected runners finishing run distance is at least, as in greater than or equal to 26.36, which, for using the tables, we want to get this in terms of a less than sign. So we'll say that this is equal to 1 minus probability of X being less than 26.36. Now we compute a z-score. So I'll do that over here on the side. We have that z is equal to 26.36 minus 26.4, all divided by the standard deviation, 0.03. So the numerator is negative 0.04. The denominator is positive 0.03. So that's the same as negative 4/3, which is negative 1.33. And so this probability then is equal to 1 minus the probability that z is less than negative 1.33. And that's equal to 1 minus, we looked this up in a table, and I don't have the table on this iPad, so I can't actually display it. But again, I wrote out these solutions earlier. So let's look at what it would be. So 0.0918. So let's go back. 0.0918, which then is equal to, I didn't even look at the last bit. So 282, 0.9082. Yes, that is correct. Okay, so let's move on. What is the probability that a randomly selected runner finishes with a running time between 26.39 and 26.43? So this is the probability of being between, so 26.39 less than X less than 26.43, which is equal to probability that X is less than 26.43 minus the probability that X is less than 26.39. Now we need to find two different z-scores. So we need to convert these both. Let's do the first one. So z1 is 26.43 minus 26.4, all divided by 0.03, which is equal to 26.43 minus 26.4, that's 0.03, divided by 0.03, that's precisely 1, so 1.00. And then z2 is equal to 26.39 minus 26.4 divided by 0.03, that's negative 0.01, divided by 0.03, that's a negative 1/3. So rounding, we would get negative 0.33. So this is equal to probability that z is less than 1.00 minus probability that z is less than negative 0.33. And again, we have to look, didn't really realize I was gonna have to be switching so often back and forth. But yeah, we have 0.8413 minus 0.3707. So equal to 0.8413 minus 0.3707, which was equal to, I think anytime I have to write, I have to switch back this way, which is unfortunate. So 0.4706. So 0.4706. Great. Now, what is the minimum finishing distance a runner could have run to have run further than 5% of the other runners? So this is a percentile problem. And just like I made on the last review with the timing being different, and a lot of other students then made on the midterm with, the fast versus slow issue. Let's draw out what the distribution would be and what would be to the left and what would be to the right. And what is this 5%? Is this 5% going to be the bottom 5% or is it going to be the top 5%? So if we think about it, this is in terms of distances, not time. So there's actually no tricks here in this case. So to the left would be less distance and to the right would be more distance. So what is the minimum finishing distance to have run further than 5%? So that means if you were right here, and this is the point where, I don't know how I just added those lines. And they're here to stay. All right. Like I said, haven't used an iPad. Don't know where they came from. So this is the point where this is 5%. And that means that if you run this distance right here, you run further than the 5% that are below you. So this number right here that we're trying to find is the probability that z being less than z, so we're trying to find the z-score, that is equal to the bottom 5%, so 0.05. And maybe you remember by now, at this point, doing all your stuff with confidence intervals, this would be the same z-score that we'd use for a 90% confidence interval. And that would be negative, so z is equal to negative 1.645. Now, what we need to do is convert this back to a distance. So z is equal to x minus mu over sigma, which means that x is equal to z sigma plus mu. is equal to negative 1.645 times 0.03 plus 26.4. And if you do the calculations here, this is 26.35 miles. All right. So let's do the last problem then. So we have that if we take a random sample of 9 runners, we want to figure out what the probability is that their finishing distance, this has a typo in it actually. So if we take a random sample of 9 runners, we want to know what is the probability that their mean finishing distance is between 26.39 and 26.43. Otherwise, it doesn't really make sense if we're not talking about a mean, because if we have 9 runners and we're saying what's the probability that their finishing distance is between some number, there's 9 of them. So there's 9 different numbers. That doesn't really make sense. So we need to take the mean. So whenever we take the mean, we knew that the running distances were normally distributed. So the sample mean, x bar, is going to be normally distributed with the same mean, 26.4, and standard deviation, that was the same as the standard deviation of x, so 0.03, divided by the square root of the sample size, which is 9, which is equal to a normal distribution with a mean of 26.4 and standard deviation 0.01. 9 is 3. Square root of 9 is 3. So we get 0.01. Now we just compute the z-scores. So we have that z1 is equal to 26.43. So that's this number right here, minus 26.4, all divided by our standard deviation is now 0.01. So this is equal to just 3.00. And then z2 is equal to 26.39 minus 26.4, all divided by 0.01, which this is negative 0.01 divided by 0.01. So this is negative 1.00. So the probability that we need to find is the probability that x bar is less than 26.43 minus the probability that x bar is less than 26.39, which we just computed these z-scores. So the reason we did that is because this is now equal to probability that z is less than 3.00 minus the probability that x bar is less than negative 1.00. What the heck just happened? That was really weird. I truly don't know what just happened. It just erased a lot of my work. So yeah, I guess I mean, it's on the recording, everything should be fine. So it was the probability that z was less than 3.00 minus the probability that z is less than negative 1.00. And now let's go back to check what those numbers are. So probability that z is less than 3 minus probability that z is less than negative 0.11 is just equal to 0.84. So you can see those numbers right there. So let's go back. So this ends up being equal to 0.84. And comparing this answer to part B. So part B, I think this was 4607 or something like that. I can't remember exactly, somewhere in the 40s. And if we look, 0.84 is much bigger probability than 0.4607. So the reason is, well, we can write this down. The probability here is greater than in part B. And this is because the standard deviation, so standard deviation is smaller for X bar than for X. So the same range, 26.39 to 26.43, when we had a bigger standard deviation, that means our distribution, the bell curve, was more spread out. So the area captured underneath the curve in that interval, because it's more spread out, more of the distribution is outside of that interval. Whereas when we narrow the distribution, that means more of the distribution is within the interval 26.39 to 26.43. So that squeezes more of it to be under it. So we get a bigger probability, bigger area underneath the curve for that same interval. Okay, and so that's the end of question 2. Any questions so far? All right, then let's continue on to question 3. So question 3 asks, well, it says, when the UCSB Board of Regents were considering eliminating the daily COVID-19 symptom survey, public health officials signaled that this would be acceptable given the local COVID case rates. But the university is unsure if students are ready. And a random sample of 324 students was conducted to determine if the students wanted to keep the daily symptom survey or if they wanted to get away with it entirely. Of the 324 respondents, 159 indicated that they would prefer to keep the daily symptom survey. At the alpha equals 0.025 significance level, test the claim that most students are ready to get rid of the daily symptom survey. So you may notice that this is actually exactly one of the midterm 2 problems, depending on which version you had. It's the same numbers as one of the versions. That's where I got this question from. I just changed it from then, instead of just constructing a confidence interval, actually doing a hypothesis test instead, but with the same exact setup. So,
Chris?
Yes.
I don't know if it's just on my end, but like my question 3 is different.
It talks about the UCSB bookstore interested in whether or not they should discontinue the emblem on the merchandise, something like that.
Oh, yes, that was an old version that I changed it to this. So yeah, I guess I just, when I uploaded the file and sent that one, I guess I sent the old one. This is the problem I'm going to be doing. So yeah, I guess you have that other problem now that you can practice on your own. I think that's also a hypothesis test problem. Is it not? Or is that confidence interval problem?
It's with hypothesis.
Okay, so yeah, then you just have another one to practice on after this. So yeah, I'm going to go through this problem. But thank you for letting me know. I really appreciate it. Okay, so the null and alternative hypotheses, we just need to set that up. So we have H naught and HA. And H naught is always going to be with an equal sign. So that's really easy to do. So this is going to be a proportion. We're dealing with the proportion of students that either want to get rid of the survey or proportion of students that want to keep the survey. So we'll say that P is equal to well, let's actually, I guess, read a little bit more carefully. Let's try to figure out what value should go here. So it says at the alpha equals 0.025 significance level, test the claim that most students are ready to get rid of the daily symptom survey. So most meaning more than 50%. So our null hypothesis is going to be 0.05. 0.5, my bad. And now essentially the claim is that we want to see if the proportion of students that want to get rid of the daily symptom survey is greater than 50%. So we'll say that P is greater than 0.5. But what we, and this is also the claim, why I am emphasizing this is we have to just make a note that that's what P stands for. P is the proportion of students ready to get rid of the survey. So that want survey gone, as opposed to the other way around, the proportion of students that want to keep the survey. And that's only just important to note, just so that we do the right P hat. So when we compute P hat, because actually when we do that right now, P hat in part B, where we're going to find the appropriate test statistic and do the hypothesis test. If we read, of the 324 respondents, 159 indicated that they would prefer to keep the daily symptom survey. So if we just went ahead and said 159 out of 324, we'd be doing the wrong test right now, because P stands for the proportions that want the survey, and what I've just written down is the proportion of students that want to keep the survey. So instead, this is actually the opposite. So get rid of that. This is 324 minus 159 over 324, which is equal to 165 over 324. And I'll just do that really quickly. That is 165 divided by 324 is 0.5093. So again, just be careful if you're reading the problem, make sure that you do the right proportion, that everything's consistent for your hypothesis test. So now we need to do the test statistic. This is just a standard chapter 8 proportion hypothesis test, which just means that it's P hat minus P divided by P times Q all over N, which everything in the denominator is underneath the square root. So this is equal to 0.5093 minus P is our null hypothesis value, 0.5, divided by 0.5 squared over 324 underneath the square root. And so the 0.5 squared comes from the fact that Q is equal to 1 minus P. And so if P is 0.5, then Q is also 0.5. And if we compute this value, I don't remember, so let's take a look. It's 0.33. And let's go back. So 0.33. And our critical value, well, if we have that alpha equals 0.25 or 0.025, and this is a right tail test because we have that P is greater than 0.5. So we're looking in the right tail area. So that means that we're looking for Z sub 0.025, which again, you might just remember this value from all these confidence intervals that we've been doing. This is the equivalent of the critical value for a 95% confidence interval, it's 1.96. And then we just compare. So we know that, again, this is a right tail test, so we can just look to see that our test statistic is less than the critical value. So we fail to reject. Fail to reject H naught. And now in part C, we need to state our conclusion in the context of the problem. So we fail to reject and here you can notice I'm not saying because P is less than alpha or because the test statistic is less than the critical value. You could put that in the intro of the sentence. It overall actually isn't too important because you just did it in the part before. So interpreting it, we fail to reject the null hypothesis. And a lot of students on the last check-in assignment wrote this first part correctly. They would say we fail or we reject the null hypothesis. And then when they wrote the context they wrote was for the alternative hypothesis. So just make sure you know what the null hypothesis is. So we fail to reject the null hypothesis that the proportion of students that want to get rid of the survey is equal to 0.5. So the null hypothesis is that P is equal to 0.5. So we fail to reject this idea, which is saying if we fail to reject the null, that means that there's insufficient evidence for the alternative. So there's insufficient evidence that, what is the alternative? The alternative is that most students want to get rid of the survey. So are there any questions about that? Cool. So yeah, again, to those that are attending and you have the link, you have an extra problem that you can work on that's basically the same and get some more practice that way. So question 4, now we have 2 independent simple random samples of motorcycle crashes in the US were recorded for 2020. One for riders wearing helmets and one for riders not wearing helmets. Among 425 accidents involving riders not wearing helmets, 61 were killed. Among the 1,280 accidents involving riders that were wearing helmets, 28 were killed. We want to see, using an alpha equals 0.01 significance level, we want to test that claim that helmets are effective in reducing fatalities. So I also hope that the other problems in this are, I'm just going to check actually, yeah. I'm going to check myself that the rest of these problems are going to be the same. I don't know what version of this exam I did. Okay. Yeah, it looks like the rest are the same. So we should be good to go. All right, and so I'm going to continue. So using appropriate notation, we need to write the null and alternative hypotheses. So let's define what our populations are, or what P1 and P2 is, or what P1 and P2 are, so that we actually write down the hypotheses correctly. So let's call, I want to get rid of that. Cool, okay, that worked. I don't know what I'm doing. It's making these, when I practiced with this earlier, it did not make any funny markings for me. You know, of course, it's just happening when the Zoom meeting is actually occurring. But oh well. So P1, population 1, we'll say that this is the proportion of deaths without helmets, or let's go with helmets. Again, I don't know why that's happening. It's really weird. So proportion with helmets. I just don't remember which one I did on the solution sheet. So if we have to go back to that, I guess I wanted to be consistent, but oh well. So population 2 would be the proportion of deaths without helmets. So again, it doesn't matter which one we call P1 and which one we call P2. That's just to lay the groundwork so that we are consistent with ourselves as we go through this process. So H0 would always be that P1 is equal to P2. So the proportions of deaths with or without helmets would be the same, as in helmets are not effective at preventing fatalities. Where now we needed to define what these populations were, because I could say P1, okay, now I don't know if P1 is less than or greater than P2 or not equal to P2. Let's figure out what it's saying. So the claim is that helmets are effective in reducing fatalities. If helmets are effective in reducing fatalities, that means the proportions of deaths with helmets, the proportion of deaths with helmets would be smaller because helmets are causing less deaths. So that means P1, in this case, P1 is less than P2. The proportion with helmets is less than the proportion without helmets. And if you want, you can rewrite these as P1 minus P2 equals 0, and P1 minus P2 is less than 0. And now let's move on. We're going to find the appropriate test statistic and perform the hypothesis test. You may use either the critical value or the p-method value. And so again, I'm going to end up using the critical value method because I personally think that it's easier. So the test statistic, well, we need a bunch of information to be able to count to be able to compute the test statistic. We're going to need the sample proportion for P1. We're also going to need the sample proportion for P2. And so let's just write what those are quickly. So P1 is the proportion of deaths with helmets. So with helmets, there were 1,280 accidents with riders involving helmets, and 28 were killed. So we have 28 over 1,280 is a proportion for P1. And now P2, again, this is why we defined it up above so that we can keep track, and we know that P2 would be then the other sample that we took. So 61 over 425. Now I'm going to write out the formula for the test statistic. So we have that Z is equal to P1 hat minus P2 hat minus what the assumed value of P1 minus P2 would be, which is 0. But I'm just going to write it out explicitly anyway. And then when we're assuming that P1 equals P2, which is basically all the time with a null and these two sample proportion problems, we don't use P1 hat and P2 hat in the denominator. We instead use this thing P bar Q bar over N1 plus P bar Q bar over N2. So let's compute over here on the side what P bar is. P bar is assuming that the proportions P1 and P2 are the same, then we could just assume that we sampled from one big population. So our total proportion of deaths would be 61 plus 28 over the total number we sampled, which was 1280 plus 425. And so this, if we actually compute this, so 80, 89 over, this would be 1705. And that means that Q bar is equal to 1 minus P bar. And 1705 minus 89 is 1616 over 1705. Now we just plug everything in. So let's just, I guess, draw a little arrow. So this 1280 would be N1. This 425 is N2. So we have everything that we need because P1 minus P2 here, this is assumed to be 0. So we have 12 or 28 over 1280 minus 61 over 425, all divided by, and then we have, well, we could factor out this Q bar, P bar, Q bar in the denominator. So we have P bar is 89 over 1705, and Q bar is 1616 over 1705. And then this would be, basically we're factoring this out, and it's going to be 1 over N1 plus 1 over N2. So N1 was the 1280 plus 1 over N2 is the 425. And then this whole thing is underneath the square root. So this is kind of a huge pain to compute, but it ends up being negative 9.77. And now, last thing we need to do is find the critical value and just compare this value, the test statistic, to the critical value. So this is again at the alpha equals 0.01 significance level. And alpha equals 0.01 with a left tail test. So because this is a left tail test, we're thinking of this 0.01 being all in the left tail. So we could find the value by going to the z-score such that the probability of z being less than z is equal to 0.01. So, and if we do that, we would get, I guess I'll write the z sub alpha here. Z sub alpha is equal to negative 2.33. And because negative 9.77, this is a left tail test. So negative 2.33 is right here. Maybe this area to the left is 0.01. And this is the rejection region. And because this is the rejection region, what's to the left of negative 2.33 is a left tail test, and negative 9.77 is like way out here, like probably even further than what I'm drawing. And it's in the rejection region, basically. So because negative 9.77 is less than negative 2.33, we reject H naught. All right. And then the last bit is then to just state the conclusion in the context of the problem. So we reject the null hypothesis. And then what is the null hypothesis in English? We reject the null hypothesis that the proportion, let's get rid of that. The proportion of deaths in motorcycle crashes with or without helmets is the same. So that is a way in English to say that the proportion of deaths with helmets is equal to the proportion of deaths without helmets. And since we rejected the null, that means there is sufficient evidence for the alternative. So because we're rejecting null means plus for the alternative. So there is sufficient evidence to support the claim and the claim is that helmets are effective. So that helmets are effective at reducing fatalities. Again, that last sentence comes from this part of the alternative. There is sufficient evidence for the alternative that P1 is less than P2. P1 means that the proportion of deaths with helmets is less than the proportion of deaths without helmets, which means that helmets are effective. So that's the end of problem 4. Are there any questions? All right, let us continue on. So this is the last free response question that I have. It says that a researcher is studying if heart disease mortality rate in the US has significantly changed over time. The researcher collects data from 5 randomly selected states. The heart disease mortality rates per 100,000 citizens for the selected states from the years 2005 and 2015 are shown in the table below. Assume that the differences in heart disease mortality rates between 2005 and 2015 in the US are normally distributed. So this is a chapter 9 problem where we're going to be dealing with differences. So the paired data. So find the mean value D bar for the differences D for the paired sample data. So let's write out what all of our differences would be. And the way that we do these differences is we pick one column to be the first column, and we pick the other column to be the thing that we subtract. So we do the first column minus the second column. It's not the absolute value. So we'll see as the first difference. So we'll have D1, D2, D3, D4, and D5. So D1 is going to be 260 minus 200, which is equal to 60. Then we have 230 minus 180 is equal to 50. And then D3, we keep the 175. Notice how 175 is smaller than 180, but we do the first column minus the second column. So this is going to be a -5, and it's okay that it's negative. And it also doesn't matter which one you did first. You could do the second column minus the first column as long as you're consistent. Just like how defining the different populations being population 1 or population 2 doesn't matter. Doesn't matter which one you subtract for the same kind of reasons. Everything will just end up working out. So then we have 170 minus 160 is equal to 10. And then we have lastly 140 minus 120 is equal to 20. So that means that D bar is equal to 60 plus 50 minus 5 plus 10 plus 20 all over, there are 5 numbers here. So all over 5. And if you compute this, you get 27. So sample mean for the differences is 27. Now we need to find the standard deviation for the differences in the paired sample data. So the standard deviation, you all may or may not remember, it's got this ugly formula, but there's only 5 terms. It's really not that bad. I'll write it out. So first it starts out with 1 over n minus 1. So 1 over 5 minus 1 in this case. And then we take the differences of our data. So D1 would be 60 minus the mean, so 27. Take that and square it. Then we add with our second difference, which is 50, subtract the mean, square that. Then we take the third distance, which is third difference, which is -5, minus the mean, square that, and add that with 10 minus the mean squared, add that with 20 minus the mean squared, and then everything is underneath the square root. Without the square root, this would be the sample variance, but with the square root, it's the sample standard deviation. And if we compute this, it's 27 point something, but I don't remember exactly what it is. So let's go look. It is 27.2947. So 27.2947. Now we're going to find a 90% confidence interval for the difference of the means in 2005 and 2015. Essentially just create a confidence interval. For paired sample data like this, the formula for it, which is on your formula sheet, is basically the same as the regular confidence interval involving t, where instead of an x bar, this is now d bar, plus or minus the same t sub alpha over 2, comma n minus 1, times now sd over square root of n. So it's exactly the same as the chapter 8 confidence interval. It's just that now our data are these differences of 2 different proportions, or 2 different of data from 2 different populations. I mean, now d bar was, or I guess before doing d bar, we need to figure out what t is. So alpha is equal to 0.1 in this case. And notice that this doesn't have anything to do with the hypothesis test stuff so far. It just says straight up compute a 90% confidence interval. So we don't have to think about, okay, do I double the significance level and go with that alpha or any of that business? It just straight up says 90% confidence interval. So alpha is 0.1. So we don't even have to think about it. And that means that t, so 0.01 or 0.1 divided by 2, comma 4. I don't actually remember what this value is. So again, I need to go over to see what it is. 2.132. And let's go back. So this is equal to 2.132. And then now we can construct our confidence interval. So this is d bar, which is 27 from part A, plus or minus 2.132 times 27.2947, all divided by the square root of 5, which is equal to, let's just look back. So 27 plus or minus 26.0244, which is then these numbers here, 0.9756 and 53.0244. So let's see if I remember that 0.9756. This is 26.0244. And that's equal to 0.9. I don't remember what this number is. You saw it. It's in the recording now. 9 something, and then 53.0244. Actually, I do feel like I need this number. So let's look one more time for the interpretation. So 9756. So 9756. And I actually didn't even need that number now that I realize, oh well. So part D, this is our final answer, by the way, right there. Part D, does the confidence interval you found support the claim that heart disease mortality rate in the US has significantly changed between 2005 and 2015? So again, we don't need to think about what the significance level is or anything like that. We already computed the confidence interval at 90% significance or 90% confidence. And we're just asked, does this support the claim that the heart disease mortality rate has significantly changed? And because our confidence interval does not contain 0, and why doesn't it contain 0? Because both endpoints are positive. So if we drew a number line, 0 is like right here, 0.9756 is right here, and 53 point whatever is somewhere out here. So our confidence interval is all positive numbers. It's excluding 0. So because 0 is not in our confidence interval, that means that there is evidence. Essentially, there is, or I guess the way to say it is the confidence interval does support. So get rid of that. The confidence interval does support that there is a significant difference in heart disease mortality in the US between 2005 and 2015. All right. So that was the last free response question. Are there any questions before we move on to the multiple choice? All right, then let's do this, and let's do these one at a time, and let's have the chat. You can message me, doesn't have to be everyone, like in the everyone chat. You can message me directly if you want. Just give me your best guess for each one of these questions. So for question 6, the 2 distinct types of categorical data are what? We have voluntary and random, nominal and ordinal, categorical and quantitative, and discrete and continuous. So what is your guess for the 2 distinct types of categorical data? Yes, it looks like everyone is putting B, and that is correct. So nominal and ordinal data. Now, question 7, if the significance level alpha is bigger than our p-value, then we accept the null hypothesis we reject the null hypothesis, we fail to reject the null hypothesis, or we just give up. Go ahead and put your answers in the chat. So let's write it out. And we have that alpha is bigger than P, which we more commonly write P less than alpha. And so there's a lot of hesitant answers. But if P is less than alpha, then what does that mean? It means, well, if we had like a left tail test, for example, remember alpha is going to be this cutoff value. So the area to the left here, for P to be smaller than alpha, that means our test statistic landed somewhere in the rejection region because the area to the left of the test statistic is smaller than alpha. So actually the test statistic is in the rejection region. So if alpha is bigger than the p-value, we reject the null hypothesis. Great. Let's do question 8. And not entirely sure if you guys actually ended up getting to type 1 and type 2 error. I think you did. So I did want to throw type 1 error into, I guess that's a type 1, type 2 kind of multiple choice question. So essentially it's just saying, okay, somebody says that you did talk about type 1 and type 2 error, which is great. So this is just asking, what is type 1 error? Type 1 error can be described as what? So we have rejecting the null hypothesis when the alternative is true, rejecting the null hypothesis when the null is true, failing to reject the null hypothesis when the alternative is true, and failing to reject the null hypothesis when the null is true. So I'll give you a couple minutes to think about that and go ahead and then put your answers in the chat. Yeah, now people are getting it. So the answer is B, rejecting the null hypothesis. And the way we could have gone about that, we could at least knock out 2 answers, right? Because 2 of these are not errors at all. If we fail to reject the null hypothesis when the null is true, I mean, that's good. If the null is true and we didn't reject it, that's not an error. And if we reject the null when the alternative is true, that's also not an error because the alternative is true, which means the null hypothesis is false and we rejected the null hypothesis. So we could at least narrow it down to 50-50. And then type 1 error is equivalent to a false conviction in like a courtroom setting. So somebody is innocent until they're proven guilty. So the null is that somebody is innocent, right? They're innocent until proven guilty. And a false conviction then means that they were deemed guilty, but in reality, they were innocent. So deemed guilty, the alternative would be guilty. So you rejected the null, which means you went for the alternative, which means you thought they were guilty when the null was actually true, that they were innocent. So yeah, it is B. Okay. Question 9. Given that two events A and B, or given two events A and B, if these two events are independent, then which of the following statements is true? Probability of A given B is the probability of A. Probability of A and B is probability of A times the probability of B. Probability of A and B is probability of B given A times the probability of A, or D, all of the above. Again, take a minute and then put your answers in the chat. Looks like we're getting mixed answers on this one, which is good. I'm glad that we're getting it. Glad to put this one on here then. So the actual answer is D, all of the above. And the reason is that these two, let's see, I'll draw these two. Always true. Doesn't matter that A and B were independent. This one is because of independence. So because of independence, if A and B are independent, for example, part C, in part C here, the probability of B given A, well, it doesn't matter that I know what A is. They're independent, so it's just equal to the probability of A, or probability of B, I mean. So we have the probability of B times the probability of A. So that gives us the expression in C by independence. And then, yeah. Oh, yeah. And so, again, actually, yeah, I said this wrong. I wasn't reading those right. I wasn't reading this top one right. This one is also by independence. So C is always true. And then these two are by independence. So this is by definition of independence, this top one. And then you're applying that in C, and you could get B. So it's all of the above. Okay, and then the last one is a terminology question. So which of the following is not a problem with sample surveys? Response bias, undercoverage, wording effects, or overcoverage? All right, that one was pretty quick for people. And yes, you are correct that overcoverage is not an issue with surveys. More data, the better. So there's no such thing as overcoverage. And that is the end of these problems that I've selected. So I'm going to end the recording now.